All right, welcome. Today, we're going to tackle one of the biggest, most powerful ideas in all of math integration. It's the tool that lets us connect something happening in a single instant to the total of what happens over time. So, how do you figure out the total distance you've traveled just by looking at your speed right now? Or how do you find the volume of a whole object just by knowing the size of one slice? Well, integration is the key. Let's kick things off with a pretty simple question that gets right to the heart of it.
So picture this. You're in a car, but you can't see out the windows. The only thing you have is the speedometer. You watch as the car starts from zero, speeds up, and then slows back down to a complete stop over, say, 8 seconds. The big question is, how can you figure out the total distance you traveled? This little puzzle right here, it's the key to understanding absolutely everything we're about to cover.
Okay, so our puzzle is all set up. We have nothing but the speedometer's reading from one moment to the next. How in the world can we possibly uncover the total distance of this hidden journey? Now, some of you are probably thinking, wait a minute, this sounds like the exact opposite of differentiation. And if you are, you've hit the nail on the head. You're exactly right. Differentiation is all about finding the slope, that instantaneous rate of change, right? Like getting velocity from a distance function. Our problem today is the inverse. It's the other side of the coin. We've got the rate of change, the velocity, and we want to find the total accumulation, the distance. So here's the real challenge, the thing that makes this tricky. The velocity isn't constant. I mean, if we were just cruising at a steady 60 miles per hour, this would be easy. You just multiply speed by time and you're done. But our speedometer needle is all over the place. It's fluctuating constantly. So how do you possibly deal with a value that's changing at every single instant? To solve this, we're going to need a really brilliant visual trick. Let's stop thinking about numbers for just a second and start thinking about shapes. It turns out the solution is hiding in plain sight as the area under the velocity curve. Okay, so here's the game plan. We can't handle a speed that's always changing, but we can handle a constant one. So what if we just chop our 8-second journey into a bunch of tiny little time intervals? We'll call them dt. Now, for each one of those tiny slices of time, we just pretend the velocity is constant. See? Now we can calculate the tiny little bit of distance traveled in that slice. It's just the velocity at that moment, v of t, times that tiny bit of time, dt. And what does that look like on a graph? It's a super thin rectangle. So all we have to do is find the area of all those little rectangles and add them all up. And this is where we take the big conceptual leap. Right now, our sum of rectangles is just an approximation, right? It's close, but it's not perfect. But what happens as we make those time slices are dt, smaller and infinitely small? Well, the approximation gets so ridiculously precise that, at the limit, the sum of those razor-thin rectangles perfectly becomes the area under the velocity graph. And that area, it's not an estimate anymore. It's the exact distance the car traveled. And this whole idea perfectly illustrates this quote. The goal here isn't to just memorize formulas. We're trying to build an intuition, to make this idea of summing up infinite little pieces feel reasonable, maybe even obvious. We're turning a really hard problem about changing rates into a much simpler, visual one about finding an area. So, we've totally reframed the problem. Finding the distance is the exact same thing as finding the area under the velocity curve. But let's be honest, calculating the area of some weird curvy shape still sounds pretty hard. Luckily for us, there's a kind of mathematical magic trick that connects this whole area problem to something way, way simpler. And here it is, the magic trick itself, the fundamental theorem of calculus. What this does is forge this incredible, mind-blowing link. The act of finding the area under a curve is the exact inverse of finding a derivative. This is huge. It means that to find the total area under our velocity curve, we don't have to sum up a million tiny rectangles. Nope, we just need to find a function whose derivative is our velocity function. We just need to find its antiderivative. Let's just lock this in, because it's so important. Differentiation slices things up. It zooms in to find the rate of change at one single moment, the slope. Integration, its inverse, does the opposite. It sums all those moments up to find the total accumulation over time, the area. They are truly two sides of the very same coin. All right, so now that we understand the why, that integration is really all about finding the antiderivative to get the total accumulation, we can finally get our hands dirty with the how. What are the actual practical tools we use to find these antiderivatives? Let's open up the toolkit.
Just like with differentiation, we start with a set of core rules. The most fundamental one is the power rule, just run in reverse. So we all know that taking the derivative of, say, x cubed gives us 3x squared. So to go backwards, to integrate x squared, we have to reverse the process. First, we bump the exponent back up to 3, and then we have to divide by that new exponent, 3, to cancel out the effect of the original differentiation. These basic reverse operations are our essential building blocks.
But what about when the function is more complicated, like a function nested inside another function? For that, we've got a great technique called U-substitution, which is basically the chain rule in reverse. The whole strategy is to spot an inner function and its derivative hiding somewhere inside the problem. By subbing in a simple variable, like u, for that inner function, you can transform a messy, intimidating integral into a basic one that you can solve with the simple power rule. It's an awesome simplification technique. Okay, next up, how do we handle the product of two functions like x times sine of x? We can't just integrate each piece separately, that won't work. For this, we use integration by parts. You guessed it, the product rule running backwards. It's a really clever method that lets you trade your original hard integral for a new one that's hopefully much simpler. The real trick is choosing which part to differentiate and which to integrate, and that iLate mnemonic on screen is a lifesaver. You pick the function type that appears first in that list to be the part you differentiate, and that usually makes the problem way easier.
And finally, for those rational functions, basically just big, ugly fractions with polynomials all over the place, we have a method called partial fractions. And what's cool is this isn't even really a calculus trick. It's just a clever algebra move. The goal is to take one super complicated fraction that looks impossible to integrate and break it down into a sum of several much simpler fractions. Once you've got it in pieces, you can integrate each one of them easily using our basic rules. Okay, toolkit assembled. We've got the theory, we've got the methods. It is time to go all the way back to our original problem and put this all together. Let's finally solve the unsolvable and figure out exactly how far that car went.
Let's bring this all home. So let's say the speedometer reading from our car's journey can be described perfectly by the function v of t equals 8t minus t squared. Now that we have a function, we can use our toolkit. To find the distance function s of t, we just find the antiderivative. So using the power rule on each part, the antiderivative of 8t becomes 4t squared, and the antiderivative of t squared becomes 1/3 t cubed. And just like that, we have our distance function.
And now for the final calculation, the big reveal. To find the total distance traveled over the full 8 seconds of the journey, all we do is plug 8 into our new distance function, s of t. And when we crunch the numbers, we find the car traveled a grand total of 85.33 meters. We did it! From just a simple changing speedometer reading, we've uncovered the car's entire hidden journey.
And of course, this isn't just about cars. The power of integration, this idea of summing up infinite tiny pieces to find a whole, is literally everywhere. In physics, it's how you calculate the work done by a force that keeps changing. In computer graphics, it's how you figure out how light accumulates on a surface to create those stunningly realistic images. In finance, it's used to model accumulated returns over time. This is a truly fundamental tool for describing and understanding our world. So, we'll end with this thought. We found total distance by summing up infinite tiny moments of speed. What other big picture answers are out there, hiding in plain sight, just waiting for us to find them by summing up their infinite tiny pieces? Thanks so much for joining me.